Hello everyone. In this video we're going to talk more about free body diagrams, FBDs. Two topics: selecting bodies, what should actually be our free body diagram, and two, making the FBD more usable. Okay, so we're going to be asking questions like, what interactions should we include? Or have to be included? Which can be neglected? Which interactions can be neglected? And it's going to introduce two ideas: distributed forces and equivalent forces. Okay, so let's start off with a sketch of a hot air balloon. Okay, so here's got a real hot air balloon. We're going to draw a two-dimensional sketch of this thing. Right, there's a balloon, it's got a basket, it's hanging in the field of gravity. All right, so if I said, draw a free body diagram of this balloon, what would you do? Probably draw the balloon, the ropes, and the basket, say those are the boundaries. But what should be driving your selection of what actually is the body is the question that you're trying to answer with your model. So, for example, if the question was, how strong should the ropes be? Or related things like, what material should the ropes be? How long should they be? What should be their dimensions? How many ropes do you need? You may want to use a free body diagram that is part of the balloon. So you may draw your boundary so that it contains the basket and some of the ropes, but not all of them. That may be appropriate. You may want to choose the balloon, the air inside it, and some of the ropes. In that case, your free body diagram would be as follows with the boundaries here. So in this case, you have interaction forces. I'll draw these to denote the boundary. You have interactions, forces that are tensions in the rope. Perhaps you have some weight here. Likewise for this, the boundary ends here at the ends of the ropes, so there's some interaction with the other set of the ropes on the outside world, and these are forces here. And so these are rope forces or tension forces perhaps, and perhaps some weight as well. Are we missing any forces? Should anything else be included? How about the air? This thing is floating in the air, so you may think that you want to put the air in some way. How about the gravitational effect of the moon? So it's night out, the moon is out, you've got a nice full moon. It's going to be some gravitational effect. Our intuition tells you that that's going to have no effect on behavior of the balloon or the tension in the rope, say. And as an aside, how could you actually test to see if that was actually or verify that that was actually the case? You would probably want to make a model with the gravitational effect and then one without the gravitational effect and compare them and see if this was actually changing parameters of interest. I would guess probably not. All right, so we were looking at the air. The question is, what if there's wind? Right? What do we do with the air? What if there's wind? Do we need to include other representations for this interaction? So in this case, perhaps we are more interested in a answer of, say, how high does this go? Right. So in this case, we may be looking just at the balloon, or we may just want to look at the balloon itself without the air inside. So in this case, our boundary would be just the balloon. And no air. So in that case, the interactions would include the air on the outside and the air on the inside. since that air is in contact with the boundary. So in this case, where the boundary is on the outside of the balloon and the inside is the balloon and the air, we do not include the interior forces on the surface of the balloon because those are balanced by the balloon pushing back on the air. So these are internal forces, so they are not represented on the free body diagram. So you need to identify the question that you're being asked, and that's going to help you pick which body you should actually take, or portion of a body you should take as your free body diagram. All right, so looking at this air brings us up to the idea of the distributed force. So if we look very closely, there are a lot of molecules of air pushing on this, so there's lots of distributed forces. So lots of discrete forces, I should say. So we're going to introduce an idea to simplify our lives or make things easier for ourselves, and that's the idea of the continuum. And instead of having lots of discrete ones, we have something that is continuous. So it's, e.g., a continuous function can describe the spatial distribution of the air, so something that perhaps is a function of x, y, and z. Okay. All right. So that makes our lives easier because for distributed forces, instead of having lots of things individually that we have to deal with, we have something that's continuous, and we can use some math. We can do calculus, right? Differentials. We can do integrals, calculate centroids when we're working with these forces. Another example where this comes into play quite often is body forces, right? So body forces by nature are distributed. Over the volume, right? So every atom or molecule of this box has some gravitational pull on it. So we can describe this as continuous, right? So this goes to a continuous function. And then we can do OUS. And so now we can do some mathematics, for example, integrals, and we can sum these up. So what would definitely make our lives easier is instead of working with lots and lots of arrows, is to work with one arrow. So if we have lots of these, we have FGI, and this is going to be the sum of all of them. I is equal to 1 to a lot. And then we can represent this as a continuous function, and then we can integrate these. Over the volume. Let's just get rid of that I. Okay? And this will simplify things greatly, then we're working with one vector. So this introduces the idea of the equivalent vector, or equivalent force, I'm sorry. Because these are vectors, right? As we saw earlier with vectors, we can combine them geometrically or algebraically. So we have a vector here, we have a force vector here. We can add them together to get a resultant. So if we had a box, and in our box we have F1, and we have F2, this is going to be equivalent oh, we turned the box a little to the side, that's okay. F3. Okay. So we do have to take a little care in this case. If, for example, our question has something to do with a small localized area. So let's take the example where we've got this box, it's sitting on a table, right? And so we select as our free body diagram the box itself, and we look at the interaction with the table. Likewise, the weight is going to be distributed along the bottom surface of the box. If perhaps we are interested in a very local area, then the effect of these forces are going to have an effect on this area. If we had done an equivalent force substitution and applied a single force, which is the sum of all of these, what's happening in this local area may look a little different. So depending, again, on the question that we're asking, the effect of using one set of equivalent forces for another may change the formulation of the problem in a bit. So to summarize, think about the question that you're trying to answer before you choose your free body diagram, and then use the ideas of distributed forces as a continuous function, or equivalent forces to make working with a free body diagram simpler and easier.